In this tutorial, we're going to look at mechanism design. When we draw and dimension a sketch, we use the geometric constraint solver. That's the piece of software that looks at our dimensions and constraints and modifies the sketch to satisfy them. So normally, we use the solver as a drawing aid. But we can use this solver for other things too. Here, for example, we have a sketch that consists of 4 lines. Each line has constant length, and the lines join up at their endpoints. So if we wanted to interpret this mechanically, then we could say that it's a linkage. Each line is a rigid link. It's rigid because it has constant length. The endpoints where they join are pin joints. They're free rotationally. So if we wanted to simulate the motion of this linkage, then we would simply drag a point. By maintaining the constraints, the constraint solver causes this geometry to simulate the linkage. If we wanted to know the path that some particular point on the linkage traced out as we moved all of the links, then we could choose that point and choose Analyze, Trace Point. So now, as I drag that point, we see the cyan curve that it traces out. We could export that curve if I choose Analyze, Stop Tracing. So here I'm given the option to export it as a comma-separated value file. It's basically a list of points. You can think of it as x, y, and z versus time. So we could load that in a spreadsheet, for example, and we could plot x versus y to get the curve that we saw there, or x versus time, or y versus time, or something else. This is a 4-bar linkage, which is a fairly standard thing. The link lengths that I chose here are completely arbitrary, but they can be rationally designed too. So I'll open, for example, this Chebyshev linkage that I drew. Here we see that the longest 2 links are both 50 units long, and then this one at the bottom is 40, and the little one at the top is 20. The point of interest here is the one at the midpoint, M, of the top link. So what's interesting about this linkage, and we'll see if we trace that point, is that it describes a nearly straight line. If I drag it further, of course, we see it's not a straight line at all, but it's a good approximation. We could solve a more complicated linkage that gives us exact straight line motion, like this Poisselier linkage that I'll show here. So this has a larger number of links, of course, and it's actually not very practical to build. But as I operate the link, we see that it traces out a perfect line. Notice that we can drag any point on the linkage. It doesn't matter where. The linkages that we've seen so far could be analyzed with some amount of effort with a pencil and paper, because there's only a small number of links. The constraint solver works numerically, though, which means that it can solve very large problems with no additional difficulty. So I'll open this modified scissor linkage that I drew, and we can see here that it is just a standard scissor linkage, except that these 2 links, instead of being pinned at their midpoint, are pinned off-center. So this is a more complex problem. It clearly does something as you drag it, but it's less obvious what. To find out, we'll trace a point, and I'll drag it. And we see that the linkage takes on a quite complex set of shapes, but that the solver has no difficulties as it moves through these odd positions, and it produces this trace for us. There's no limitations beyond certain convergence issues and the speed of your computer on the number of links that can be simulated. In general, any mechanism that's actually practical to build is trivial to simulate. So far we've looked at linkages that have rotational joints, but we can also simulate mechanisms with slides, translational joints. Here, for example, we see two sliders. So these two horizontal and vertical lines represent the axes along which we slide. They're the track. Then this link here is the link that moves. So as the link moves, this point stays on this track, and this point stays on this track. So if I drag, then we can see that the constraints are respected. So here we have two linear slides, and if I want to know the shape that it traces out, then I operate the linkage and I see that the shape is an ellipse. In fact, it's a perfect ellipse. You can show that. We can combine mechanism design with solid modeling. So here I've begun by drawing the backbone of the mechanism. If I wanted to implement it for real, then I might represent these two tracks, for example, as a block with a couple of dovetail slots. And I've drawn that here. So this is an assembly. We've imported the part that I drew here with the two dovetail slots. Then we might import a couple of dovetail slides that fit in the slots. And we can see those here too. So we now have solid geometry that is tied to the mechanism. If I zoom out a bit and I operate the linkage, then we can see that as I operate the linkage, the imported parts move too, because they're constrained against the linkage. So this is a good way to test out a linkage. You can actually drag it through its full range of motion and verify that everything can be assembled and nothing interferes and so on. So far, when I've dragged a linkage, I've just done it with the mouse. So the trace that I got certainly describes the path that whatever point I was interested in moves through. But the speed along that path was erratic. It was just whatever I happened to do with the mouse. If we're plotting, for example, x versus y, then that doesn't really matter. That just means our points are spaced unevenly. But if we're plotting x versus t, then it means that our plot is meaningless because it depends on how fast I dragged with the mouse, and we don't know that. Instead, we may want to actuate the linkage by stepping a dimension. So I'll draw a trivial linkage here. This line segment has constant length, so as we drag it, it sweeps out a circle. To constrain it, I'll further say that the angle between this coordinate axis and the link is fixed. I'll put it at 10 degrees. Now, I'll choose the dimension, and I'll choose Analyze, Step Dimension. So here, I'm given the option to specify the start, which I've already done. It's just whatever the dimension is now. And specify the finish, which I'll say is now 170 degrees. And specify the number of steps, and I'll say 300. So I'll drag this off to the side so we can see, and I'll trace this point, and I'll step the dimension now. So we can see that that dimension has been stepped smoothly from 10 degrees to 170. So if we were to export the trace that we produce now, then we would see that it's actually a perfect cosine and sine wave for x and y, because we moved at constant speed along the circumference of that circle.